Do you see my the screen? Yes.
Yes. Mm-hmm.
Okay. So I thought it would be a good idea to speak a bit about work on extensions of the Amari model we did over the last couple of years. So I will show some results of mathematical analysis and also some applications. I mean, everybody who has experienced, using Amari model for modeling cognitive functions or implementing cognitive functions in robots, I think it's fair to say that everybody has experienced limitations and problems. For instance, last session, John spoke about the difficulties to model this dip in the plateau activity of the fMRI data. So it's just one example. I'm not claiming that I have the answer to it, but just to say we are faced with problems. In our case, we were not very happy about the fact that the creation of a bump, of a localized activation pattern, is all a none problem. I mean, you can create a bump with any suprathreshold transient input, but the bump is then, the bump shape is stereotyped, so that is exclusively defined by the recurrent interactions, and there is no signature of the input which has initially driven the bump. So this was our problem. We wanted to face this and come up with a problem, with a solution. So I start here with, moment, next slide. Okay. I start just like we start when we introduce this basic concepts of DFT. We have here the computational principles of lateral inhibition. So lateral inhibition stops the spread of excitation and is responsible for the stability of the bump solution. So we have a tight balance of excitation and inhibition at the bump boundaries. We have here the figure. Actually, these figures I borrowed from some of Gregor's old presentations. So we have here the notion of a bump specifying a specific value of a continuous dimension. And here on the left, we have an activation pattern that we use to show, okay, we want to express something like certainty or probability. And this, of course, is not a stable solution of the Amari equation. So when I did the work on movement preparation with Gregor more than 25 years ago, actually it's more than 25 years ago, I had to invent some shunting inhibition mechanisms to approximate such a distribution which reflects somehow a probability in a two-choice task, probability or frequency. Yeah, but again, it's not a stable solution of the Amari equation. Now, if you look on persistent population activity and experimental evidence, then you see that there is stimulus dependence. Already the early work by the Goldman-Rakic group, they showed that the level of persistent activity during the delay period of a VM task correlates with stimulus contrast. There's also the idea that the neural representation can be enhanced by top-down modulation when one of the items in the working memory becomes task relevant. Yeah, ratio queuing is here the key, the key word. So it leads to enhanced population activity. And in general, we can say that bottom-up and top-down evidence may affect the quality or fidelity of working memory representations. There's also much going on what concerns the dynamics of persistent population activity, stimulus-induced persistent population activity. It's not like suggested by the static bump, a static phenomenon, but there's a lot of fluctuations during the delay period. Often this fluctuation is systematic, showing a ramping up or ramping down. And this ramping activity has been associated with the processing of other stimulus attributes. And in my case, I will speak a bit about time as a second dimension. Then something what was also captured our attention was persistent population activity associated with learning. So if you speak about value-based decision-making in uncertain environments, there is a need of a temporal integration of behavioral outcomes yeah, the choices and the successes or reinforcements. And this takes place over quite long timescales, over several, let's say, tasks that may occupy several minutes or even half an hour or whatever. So when we do our robotics experiment, this is the case. So we have to have the capacity to maintain and modulate on very long time scales this persistent activity. So the message is it's much more dynamic and much more fluctuations than just static bound. So if you look then in the what we know about the microcircuit of spatial working memory, there is of course the idea that you can implement something like effective like lateral inhibition, but there's really a wide diversity of inhibitory interneurons. They receive input from nearby excitatory neurons and also show spatial tuned persistent activity. Some really have this inverted tuning curve. This has been associated with disinhibition mechanisms. So I think it's fair to say it's not really clear what the contribution of all these inhibitory interneurons is, but my message, or we took this as a message, that you can think about a bit more complex circuits that can do more than just what you can do with lateral inhibition. And our objective was to create actually a two-dimensional continuous attractor. So not only continuous in position, but also in amplitude, so that we can express and hold population activity at different levels of activation. So we came up with this.
May I ask a question? So this is notion of line attractor where the activation is the working memory. Is that related idea? Or
yes. It's related, but it's very well known that a line attractor only works if this precise tuning. So the big problem was that it's actually it's hard to get. So we need really a robust mechanism. So people have introduced other mechanisms like bistable units and some scaling factors and so on. So a lot of work on this, but these are extra mechanisms. We wanted to do it within the DFT framework. So this two-field model, so what we wanted, the bump shape should reflect to some extent input characteristics beyond position. And it should be a model of robust neural integrator of external inputs. And as you see here, we wanted to stay close to the Amari equation. Actually, what you have here, two coupled Amari equations. So this is just forget the red parts here. This is this coupling term. So really the Amari equation where we have here the threshold parameter theta. This is actually mathematically equivalent to the H parameter in the Amari equation. It's a mathematical thing, but it's essentially the Amari equation. And then you have this local feedback loop. So the V population integrates the U activity with the same kernel, which could be any kernel, lateral inhibition, Mexican head, oscillatory connectivity, anywhere, and feeds it back to the U population. So there is this local coupling, which actually guarantees that there is a tight local balance between excitation and inhibition, which is essentially then responsible for stabilizing activity at any level. So just a word.
Yeah, I'm confused. I mean, are you saying that without the red terms, this is the normal two-layer?
Yeah, the normal.
But where's the inhibition? Wouldn't the?
No. This is actually this minus H. I mean, this is actually you just have a coordinate transformation U minus H. If you use this, then mathematical, this is the equivalent. You can shift the non-rarity with the threshold. Or so the H parameter defines the resting state. And
what confuses me though is, so I'm ignoring the red terms, right? And if I look at that, then it looks like U is exciting V, but V is not coupling into U at all.
I mean,
there doesn't seem to be any U term in the V term in the U equation, except for the red terms, right?
No, yeah. That's exactly this. They only ignore the red term here.
Yeah.
And then it's the Amari equation. And now you have the linear term from the V equation. And here you have the linear term from the U equation. So this is a local coupling of activity from V to U and vice versa.
But in the Amari
I mean,
in the two-layer
Amari.
are these two different fields, or is V a inhibitory field?
Now, actually, it's a bit more complicated because if you think about Amari, you have already two populations, excitatory, inhibitory. So if you would create a picture of it, the architecture, it would be a 4-population model.
4 population.
4.
Yes. Okay. So V is an excitatory population as well.
Yeah. There's both. So
and
actually,
why is V? But V is inhibited by you, right?
No, I mean here you integrate the U activity with the inverted Mexican hat, and then feed it back to the U population, and the inverse is true. I mean, just saying, these are two Amari equations which are coupled linearly here. So if this would be a nonlinear function, FV, FU, you would introduce something like a saturation for the neural integrator. I mean, we did this. I have a couple of papers at the end where you can read the analysis and so on. The point is that you can do all the battery of mathematical tools that has been used for the Amari equation, obviously also for this coupled system, and can understand it very well in terms of pattern formation and so on. So the message is that two coupled Amari equations, and this is my hypothesis now, they do the job they want. I show now in the next slide the analysis of bump solutions. So we have done this for the 1- and 2-dimensional case, existence, stability, all the stuff have we done. So I show you just numerical bifurcation. Numerical bifurcation with theta, the threshold as continuation parameter. It means you create the solution and then track numerically the existence when certain parameters change. And what you find here, theta is the threshold parameter. You find here, these are two rows. Actually, the quality shows the same behavior. Yeah, just the input strength is different. The input which has triggered the bump. You see here the coexistence of an unstable and a stable bump, like in the Amari case. It looks a bit different for different on the strengths. Yeah, they coexist in the same parameter regime. And in addition, because of the local feedback group, you have also a stable subthreshold bump. That is quite different to the Amari equation. Yeah, so these are the solutions. These are, if you look compared with the Amari solutions, you would just look on the solid line. The dashed line is the V equation, which balances locally the excitation and inhibition. Yeah, so this is a solution, a stable solution, a stable bump solution. So bumps with input characteristics. This is what we wanted. You wanted a 2-dimensional continuous attractor, position and amplitude. So you have here inputs with different strengths, and you have two stable solutions. So this system is able to stabilize, obviously not the case in Amari, stabilize in the range of interaction, I mean, two bumps with different amplitude. Here it stabilizes two bumps with different widths, which is quite interesting if you think about our pre-curing experiment where you want to have, let's say, a broad initial distribution showing interpreted as a prior information. Yeah, but here it's not a pre-shaping the sense of a transient solution, but it's really a stable solution which is wider than the other. Here on the right, we have examples of the robust neural integrator. In this case, what is shown here is the time axis and the bump amplitude. And what you see here is an input which is ramping up, so increasing input strength. Now the integrator integrates here, the input stops and has reached this saturation level and remains stable there. Here in this case, we have two sequential inputs. The first one, the bump reaches this level, then the second here, the second interval, a second input is given, then it ramps up and settles down at this level. So we have really evidence for a continuous integrator. Now, to show a difference to the Amari equation, we did this really in detail to compare it, because if you can use the same parameter settings and just look on the U equation of the two-field model, and then couple it with a V equation and show the difference. So it's well known, okay, if you add additive noise, especially correlated additive noise to the Amari equation, a bump will start to drift. Yeah, and there's this nice examples from the Barcelona group showing that really this bump drift is correlated with behavior in the monkey experiments. Yeah, so you have here the heat map, it drifts. You can describe it as a diffusion process, meaning that the variability increases with time. Now, because we are able to manipulate the quality or fidelity of the memory, we can try to use bumps with different amplitudes, meaning that they represent different input strengths. And then what you see here is that the stronger the input, the higher the bump, the less is the diffusion. Meaning, I mean, maybe intuitively clear, I don't know, a stronger memory is less affected by this kind of diffusive error, let's say, with it's introduced because of the diffusion process. So this is just one example. The next one is multi-item working memory. You can think of is a two-dimensional extension of the model. Yeah, let's say representing position and orientation here. Now we have a sequential presentation of three identical, in this case, weak inputs. In general, the two-field model behaves like the Amari model, but because we have also a spread of excitation with the same kernel parameters, it's somehow facilitated. It's easier to create a multi-bump pattern with the two-field model than for the Amari model alone. But what you see here is that there is still competition. So the first two get super-threshold representations, but here with the circle, maybe it's hard to see, you see a sub-threshold represented because of the accumulated inhibition from the existing bumps. This second input, which is identical in strength to the others, does not reach a super-threshold level. But because this is a stable solution, a sub-threshold stable solution, you can recover with an unspecific input the position information. Imagine you draw attention to the position where the object was presented. Yeah, you can, with this unspecific input, just position, you can, of course, you can create again a bump, recover the bump, and of course you can read out also the orientation information. So a main message, because I mean people who advocate to activity-based working memory representation, and especially multi-item working memory, they are faced with a problem, okay, or with people arguing that actually only the item currently under attention is an active state, and the others are in an actively silent mechanism. So synaptic facilitation as a different mechanism for working memory is here the key point. So we don't need to postulate this. I know that Sebastian, for instance, in his work has shown that the fMRI data they use as to say that there's a need for activity silent mechanism, that this data you can also explain with activation-based representations. But for the Amari case, of course, this suppressed representation would go to resting state. Yeah, so the memory would be lost at all. But here in this case, we can recover this. This is an interesting point, I think, because in literature, if you look, you find really examples where they analyze sub-threshold inputs that would pass without consciousness. But still, if you pay attention to the position where the sub-threshold input was given, people are able to recover, for instance, the orientation information of this object. Yeah, so we don't need activity silent mechanism. We can recover here, let's say, suppressed activation to an active state. The second point, I think, which is also a severe criticism in my mind, is structural stability. Yeah, if you at random spatial fluctuations in the connectivity profile. This is here cross-section of a 2D type Mexican head type interaction connectivity function. Yeah, so which is a lot of noise. If you add noise, of course, you destroy the symmetry and the continuous attractor is gone. Yeah, this is a central criticism. So in the Amari model, for instance, if you initialize at 0, you will see a drift to a certain position. You can show that actually there's a finite number of possible positions where this in the representational space where this bump will drift. If you run this 100 times, this figure with the outward trajectories where the bump will settle down. If you use now the coupling of the second equation, you see a kind of distortion of the shape, but essentially it keeps there, it stays there. So if you now have the same simulation as before, which is looking on the outward trajectory, you see it stays here more or less at 0. So with this severe perturbation of the symmetry, you still get a bump which is essentially remains localized at the initial position. Yeah. If you make a cut here, you see, if you look, okay, in epsilon direction, there's a slight change, a small error, but it's essentially stable. So this is a central criticism. Yeah, why people are arguing we need other models than this kind of bump attractor model, which heavily rely on the assumption that you have a perfect symmetry in your interaction. We have also tested other perturbations, let's say non-radially symmetric kernel functions or spatial bias and so on. And in essential, we get the stability.
I don't know, do you want a mixed discussion or you want to do the discussion at the end?
If you have asked questions, ask. I mean,
I think mathematically, of course, an interesting challenge. I mean, with John, we have sometimes argued that the drift we observe of peaks in working memory is real, that in behavioral data we see such drifts. Or is that a different problem, or is that
no? I mean, I have shown this here. I mean, this is a drift here.
Yes. Yeah.
Yeah. But
so the drift and non-robustness is that different?
Yeah, the non-robustness is about the assumption that a bump attractor only exists if you have a perfect symmetry. I mean, really perfect. Any small perturbations of this symmetry will destroy this. So all your interaction effects, repulsion and whatever, will be gone, actually. So this is additive noise, which leads to a drift, which is observed in the experiments. But the other is something about structural stability of the model. Yeah, if you perturb, let's say, somehow the symmetry of the interaction kernel, and this is the argument, this is not biologically plausible that in the brain you find this perfect symmetry, and any small perturbations will destroy it. I mean, this is not.
Can you explain that again? So when you say that if the kernel is a little bit noisy, in which sense does it destroy that? Can you explain that?
Yeah. So this will really wander to any position. You didn't control it. I mean, not any position. So it will wander really not a small deviation. It will continue moving to no one knows where. I mean, settles down.
Is that different from the drift? I mean, would that be empirically different?
Yeah, because it's really a strong effect. It's not just a small controlled effect of a diffusion drift, which you get with this additive noise. This is really something, if you want a large field, it would move to whatever position. It has nothing to do with the initial position. It's not just a small drift.
So are you saying in this figure, if you had noise on the interaction function, and I'm seeing one type of noise in panel G and the other type in panel H, are those the examples?
No, this is a noise here. This is the noise. This is a cut cross section of the 2D.
I think we don't see your mouse, so you might have to refer to the label of the figure or so. I don't think we see your mouse, or does anybody see your?
No, A and B. Yeah. Figure A and B are cross sections of a 2D kernel with noise.
Okay.
Yeah, actually, this is borrowed from a paper that people who advocated that we need synaptic mechanisms for working memory. They use this. We copied this. Use this as an argument. This is not structurally stable. Yeah, and it's not biologically realistic to assume a perfect symmetry. That is, I mean, we have even used here the parameter settings they used to argue that, of course, this bump attractor model has done a lot and whatever, and it's not totally wrong, but it's not realistic, and we need other mechanisms for working memory. That's their argument. Yeah.
I guess the point I didn't understand, if the kernel has this funny structure, so again, can you say what the symptom is? So how?
This was initiated here, and after some time, the bump appears here, and if it is bigger, it will appear here or whatever. And the next run, it will appear here, and the next run, it will be appear here. So this is.
We don't see what you mean by here.
We don't see your pointer. You'd have to.
C and D, sorry, I thought C and D. Yeah, this is Amari. There's a difference between the Amari and the two-field model. Here, you can say there is some drift, some small drift, even with a lot of noise in the kernel, a break of the symmetry, and it still stabilizes the bump at the position. There's small fluctuations. In the Amari case, it destroys totally the continuous attractor. So this bump moves to any position.
Well, I think the difference is between this drift due to additive noise from the input, and this is that this is a directed drift. If your kernel is asymmetric, then it should, as you said, you create this number of discrete attractors in your system, and they have kind of some basin of attraction. Every time your peak will drift towards them.
Yeah. So it's really just to say, I mean,
bias.
Yeah. What I just wanted to say, that is a criticism of people who have argued against the bump attractor model and say we need, because of this, different mechanism. Because it's not realistic, biologically realistic to assume such a fine level of fine-tuning in the recurrent interactions, so that you can guarantee.
This is, I think, a interesting debate that I was hoping maybe we have afterwards, which has to do with how do you ground your concepts? So, for instance, do you say, well, this is how neural networks really are in the brain? And when we go to this equation, we'd have to ask these questions as well. And I guess our line of argument has been that what we know about neural networks is consistent with some imprecisions that we see, working memory not being perfectly stable over a longer time,
but this is really, I think, a difference to this diffuses drift that people argue and have argued that is realistic and nice and whatever, to this kind of, this is really a model assumption, structural stability. For instance, we can use the sigmoid function or the step function and get more or less the same results. That is structurally stable. Here, if we show this kind of random fluctuations or spatial bias or whatever, that actually we assume if you would learn this kernel, no one would assume a perfect symmetry, for instance. I come back to this point. So my point is, our model, which has these nice properties to be a robust neural integrator, that's what we need, also shows the structural stability. So if we can live with a lot of fluctuation or whatever, so this was an argument that you still can live with this DFT framework in the sense and activity-based modeling of working memory without the need to assume totally different mechanisms, like, for instance, synaptic facilitation. So that is, in my view, the good message. Yeah. So this is an additional point that has been criticized. For the modeling, we are much more interested about this to have some signatures of the input in the pattern or have the neural integrator. That is functionally what we need. But in addition, it's much more robust, structurally robust, the model. That's my message, nothing more. Now, just to show some applications we were interested in. So we were interested in the question of timing. how are monkeys or biological systems able to measure and reproduce time intervals? And there's an interesting experiment by the Shetland group. Actually, they use then the notion of neurodynamics to explain this. But the experiment is the monkey has to measure and measure a time interval, different time intervals, and then immediately afterwards reproduce it, and at the end make a saccade. So there are two cues. The initial cue for the starting of the time interval, and then in the middle you have a second cue saying, okay, stop, this is the end of the measuring period, but this cue immediately serves as a cue for starting the reproduction interval. And what they see is that there's a ramping activity in LIP, and the activity at the end of the measuring period is proportional to the duration. The higher the interval duration, the higher the activity. And then during the reproduction period, you see here ramps, but with different slope. And the slope, obviously, is inversely proportional to the maximum activity. The longer the interval, the shallower the slope. So this is linked to the saccadic onset also. There's ramping, but with different slope. And so if you have ramping activity, you can explain it with the integrator simply. And here is just an experiment. So you have the bump with different height, representing in this case the measured interval. Here you see this ramps up and settles down at different levels, and they are proportional to the. You cannot see this here in the middle panel here. It ramps up and settles down here in the middle panel. And on the right here you see that the sample interval correlates well. It's a linear increase with a bump amplitude. During production, in the upper panels here, you see here a readout threshold. It reaches a certain threshold. The assumption that a certain threshold is reached, and then the saccade is made. So it reaches at different levels. And so if you plot here the sample interval against the production interval, you get also a good fit here. Yeah, so the neural integrator works well qualitatively reproducing the experiments as I've shown in the monkey experiments. So next example is what we are doing now quite a long time, human-robot interactions. So we are inspired by human-human interactions. So I worked a lot with people from psychology to learn something how it works in humans. Now you see here our industrial robot Sawyer learns a sequential order by observing a human team. So it's an assembly task, a pipe assembly task. You see here the human team assembling together this pipe ensemble. One is the giver, the other is the receiver, and then also mounts doing the assembly work. So the robot will then substitute the giver, and try to do it in the correct order. So during joint action execution, the robot hands over to the human user the different pipes in the correct order. That is our challenge. Now, if we can, we can stabilize bumps with different strengths. What is the idea here is during observation, you see the manipulation of the different objects. Actually, they are specified by color and length here. It's a two-dimensional representation. A different snapshot, 11 seconds, 53 seconds, and so on in the real experiments. There's a handing over of different objects. What you see here is that during the handing over, there's the representation emerges, in the memory, a bump representing this object at this time. And after successful completion of all handing overs, you have here this multi-bump pattern with different, each pattern a peak with different amplitude, where the amplitude strength here reflects the order. The highest is the first, the second, third, and fourth. So you have during the encoding phase the time course of activity in the memory field. There's also a start and a stop signal saying, okay, this is really a start of the sequence and a stop of the sequence. And you see here at the moment that there's a ramping up of activity. No, the visual information starts the creation of the bump, which then continues to increase until the end of the sequence. Yeah, and at the end you have here different bumps with different activation levels. Now the idea of recall is that this memory information is a pre-shaping input for a decision field. Yeah, you have then a gradient also in the pre-activation. And then we have a simple release of proactive inhibition, meaning that we actually have a H, the resting state dynamics, so that the activity globally in the field increases. And when the activity of the highest bump here in the pre-shape reaches a certain activation level, the activation is started. Yeah, so this is a motor readout of this memory information. So it's an autonomous recall of the sequential order in a decision field. You see here the time course of activation of handling the different objects. Yeah, for instance, at t86 seconds, you see here that the robot starts to manipulate, holds out already the blue object, where the floor in this case is still mounting the yellow one. Here you see the moment when in the decision field, the first bump penetrates the threshold. Yeah, and here you have, let's say, the memory of already executed object transfers. Yeah, these are these dashed lines here in the first panel, A, which actually is a negative feedback, which brings down the activity in the decision field. Yeah, you can autonomously recall the sequential order in the decision field, first observing, so as a fast encoding, and then an autonomous recall of the correct order. Now, this example shows that actually the robot is proactively handing over. So it holds it out when the user is still mounting another object. That actually is not the ideal case, because many users say us, we have user studies, I don't want to work under the pressure of the robot. I want to work on my own pace. So ideally, there should be no waiting period at all. So the two hands should achieve and arrive at the same time at the exchange position. So no waiting time, but also no pressure. Okay, please give me take the object. So here in this panel, where the waiting time at the exchange location, if you look at the camera view, here in A, the human is holding out the hands, showing, okay, give me the object. And the opposite is here, so there's a waiting time. And in B, the opposite, the robot already holds out an object when the human is mounting still another object. So in this case, objects and hands are color-coded, yeah, so it's easy for the vision system to detect this in the scene. So what is the essential new thing here? So we want to fine-tune the timing, not proactively, but really minimize the waiting time for both agents. So we have here feedback layers. Feedback means activity here when the hands reach the exchange position, there is a bump activation going on. Yeah, and if there is a temporal difference or mismatch between the evolution in the two feedback layers for agent 1 and agent 2, there's an adaptation of the memory strength in the action onset memory. Yeah, so what we do is to modulate the pre-shape, because the pre-shape level, the difference between the pre-shape level and the threshold for initiation the movement defines the timing. So if we change the pre-shape, yeah, increase or decrease it, we change the timing. So this is here a mechanism, yeah, the observed temporal mismatch drives an adjustment of the motor memory strength. Importantly here, this is really has to be an internally triggered cognitive motor timing signal, and there's evidence also in neurophysiology for this, because there's in the environment, there's no, no cue which will indicate the robot, now move, because it guarantees you that at the end, both hands for a human and robot arrives in synchrony at the exchange position. So there's no, no external cue or visible external cue, or you would need really to learn it, and it may be very difficult. So it's an internally triggered a cognitive motor timing signal. So what you see here is just an example. Here you have the pre-shapes in trial 1. Yeah, the pre-shape, so the order is done here. But what you see here on the right is in the first panel here is that this yellow line is where the time, this is the time axis, where the robot starts to move. And you see here the evolution. It's hard to see, but you should see it here. The red circle here indicates, okay, there's a mismatch in the temporal evolution of activity in the two feedback fields. So actually here the human activity is earlier than the robot, meaning that the human hand arrives first. So now we adjust the strength here with these adaptation mechanisms. So actually increase a bit the pre-shaping here of this. And now you see that the activation evolves in synchrony. Actually, the robot, if you show this line here, starts a little bit earlier, the movement, and this leads to a perfect synchrony of the arrival times at exchange position. So if you do it in 3 trials, we have adjusted in only 3 trials all 3 handing overs. Yeah, so they are all now occur in synchrony. Here in table 1, you see the change in 3 trials. There was minus 17 means the human had to wait for the first object 70 seconds. In the third trial, the robot waits 2 seconds. Yeah. For the second object, the robot had to wait 6 seconds, and this is in perfect synchrony in the third trial. And in the for the third object, the human had to wait 9 seconds, and after the third trial, only 1 second. So we can use here in very few trials, you can achieve a quite high synchrony for the handing overs. So the last example, quite very different. Now we have an example inspired by experiments in monkeys and pigeons and whatever, where the agents are forced to make decisions in uncertain environments. Now it's a simple 2-choice task. Here, a robot scenario, a mobile robot has to pick up either at location A or B a certain object, which may appear with a certain probability in a fixed period of time delta t. Yeah, so this probability of appearance in location A and B are not correlated. Maybe we have, for instance, in location A 30%, location B 40%, or 50-20, 30-70, so different probability ratios. We have worked with stationary as well as changing probability ratios. So it picks it up and brings it to the upload area. So this is kind of a robotic experiment. So what we wanted to show in the stationary environments, the known matching law is the optimal behavior. The fraction of choices made to an option will match the fraction of total successes or reinforcements earned from that option. Yeah, and of course, this decision in this uncertain environment depends on past choices and past successes. So we have to integrate over several trials on the past choices and successes to make an informed decision. And what we want is to have an optimized search behavior, yeah? To find as many as objects in a certain time interval. So we have, let's say, an experimental duration of t, and we divide by n, so we have n intervals of length delta t here. And in every interval, the robot has to make a decision to go to location A or B. Now, value-based decision making. Now we use our integrators. This is a decision field to make a decision to A or B. Yeah, and now we integrate the successes over several past decisions and the choices. So this activity here in this decision field is integrated here in the success field and the choice field, depending which choice and whether I had success or not. And then the feedback is here excitatory from the success field and inhibitory from the choice field. And this is necessary because we want to force the robot or the agent to also look from time to time to a location where the probability is very low. Yeah, and these are the results. So what we wanted to have an effective effective searching. Total success, what is defined as search efficiency, total success achieved divided by the number of available objects. And here you see the results of the DNF model, yeah, with different probability ratios. Yeah, the probabilities are independent. Here it's complementary to 30-70, but we have also 50-20, 60-70, 30-30, and so on. And even with small probabilities, we have really a high search efficiency. We compared it because it's done in the literature with just some simple other strategies. This most likely choose location with higher probability, or the win, stay, lose switch strategy, stay at the option if successful and change if not. And you can here find that, okay, the DNF model outperforms the other alternatives. And in addition, we have that the distribution of choices generated by the DNF model closely matches the success ratio, meaning that we have a good fit for this matching goal. Okay, the ultimate.
It's supposed to be only 20-minute talk, so
yeah. No, I will. This is the last slide, just okay. to give you an idea. I took this advantage. I mean, because many of you might not be aware of what we have done, so I think I wanted to give just a broad overview about how we applied. Current work. I mean, we are faced as modeler, but as modeler with this data-driven approach, deep neural networks. So I would say it's really, it's not modeling, it's really give me data, then use hundreds of master students to tune the parameters, hyperparameters of the network, and then everything's done. So we don't need anything, the system will learn, and then it's done. So what normally you need, a huge amount of stationary data to do this. And we are doing in a different context, learning driver routines from GPS data. We want to address the problem of continual learning with small data. So we have done this. So it's really application driven, but we use here the dynamic field framework for continual learning with small data. We need little examples to do a reasonable job in predicting, for instance, where to go, how long to stay, and so on. The second thing we are doing, bridging the gap between deep learning and DFT. So learning the continuous attractor or self-sustained activity patterns from real data, meaning that now, because we don't need this perfect symmetry in our model, we can really try to learn really from data, somehow a noisy interaction kernel which still is doing a good job. Yeah, so if you assume you want to have this perfect symmetry and learn it from data, if you learn, let's say, more examples from the left, from the right, you have immediately a bias. It will not be a symmetry, and it will not work. So this is theoretical and application work where we try to use deep learning for reduction of dimensionality. Yeah, we start maybe on the vision level with pixels and come up with latent variables, hopefully, that are continuous and can be used for the dynamic field approach. We have also some things going on, a theory of magnitude. We were interested to use the integrator model to model discrete and continuous dimension, like the sense of number, object size. So the idea is to map accumulated activity on space, yeah, to have something like a number line and so on. And we are continuing, we are making a continuation of our HIR studies where we try to implement high-level cognitive function like intention prediction, error monitoring, or as I just sketched, value-based decision-making. Last slide, if you are interested to have a closer look, there is just amid this for completeness a list of recent publications where much more details can be found about what I've spoken. So
Great.
it was longer maybe, but I thought it might be useful.
It certainly caught us up on a lot of the work that's happening in human eyes, which is very interesting. In the spirit of the kind of discussions we have in this group, I wanted to ask about sort of the theoretical position. I think you illustrated very clearly in these application examples what particular sort of functions you want to realize with these effects. Could you just show us the basic equation again, the first, like on the first slide or the second slide? Yeah, so in the, I'm asking this question sort of to say, what is DFT for, what is its position? And I would say we've had an argument that we take certain abstracted neural principles, idealized neural principles, populations, certain generic cortical coupling structures, certain properties of, for instance, the dimensionality, localist representation, so on. And then we argue we can reach cognitive function in certain idealized cases. And now, if I take a model like that, we would say, well, there is, for instance, coupling of what you call linear coupling, which means that there is coupling between neural populations that isn't going through a sigmoid, so that somehow let me just ask this question. Yeah. So that can change sign. So okay, that would be maybe not compatible with a certain neural principle. And then there is, I think, a violation of Dale's law, and that U is positive for one and negative for another. So what's the attitude to that? Is that to say,
yes. I mean,
it's just another approximation, or is that to say stepping outside that philosophy of?
No, I mean, yes. I mean, it could be a nonlinear function. Yeah, it could be not a linear. It's a matter also of mathematical analysis. We did the mathematical analysis on this. If you use a nonlinear function here as a feedback, put the activation through a nonlinearity, it becomes more biological plausible in the sense that we would have a saturation of the integrator. So it saturates at a certain level. So that would be more plausible. You still get in a certain range the continuous integration, but then it sets.
So, I'm asking a little bit more abstractly. I just want to make it concrete.
Yeah.
In more abstractly, the question is this about sort of nonlinear dynamical engineering? I'm saying I have a certain functional constraint. I build an equation that does that, or it's still a constraint that you, for instance,
because I'm using. I mean,
no problem. Just give me a second to announce my question. So, the other idea would be to say, well, we're really constraining the dynamical models that we allow by saying, for instance, that neurons have only this minus U term, and other than that, they only can interact through synapses, which are captured in this approximate by sigmoids and so on. So a particular set of principles that we sometimes announce, like in our books, we've announced these principles. Are you saying that is not, that one needs to move beyond that? Or are you saying we're adding new principles to that?
No, I mean, actually, I mean, we are speaking about Amari equation. Yeah. So the principles of Amari are there. I mean, there's a local kind of kernel which integrates from neighboring neurons. There is the nonlinearity. So, of course, Amari already joins the two populations, which is maybe not biological plausible, but also in the Amari equation, there are assumptions that you have here violations of certain biological features. But because we have here Amari equations, which actually are concerned with stabilizing localized activation patterns, I mean, the principles are exactly the same. Yeah, of what is written here on top is that the Amari, we thought, okay, as I thought, I mean, there are many more interneurons. I mean, one can think, if I want, about a more sophisticated biological model, which maybe writes the equation with 4 populations and whatever, yeah, and may try to map it on neurons with inverted tuning curves, and so all this what has been described in the spatial working memory circuits. Yeah, this is just there's more space for doing things than just lateral inhibition.
So you're
And
hinting that one can actually give neural justifications.
Yeah, we need some local balance of excitation inhibition, not just on the bump boundaries, to stabilize, let's say, a persistent activity at different levels. And this is what you find in the data. No? It's not a stereotyped bump, which has no signatures at all of the input, which has driven the activation. Yeah, so if you assume this, okay, we have this kind of bump, it can do a lot, and we have done a lot of work with it. But I would say from the principles, I mean, this is written in a sense that it facilitates exactly the analysis. We did a lot of analysis. There was mathematical work involved. You can write it differently and maybe make an effort to write it as a 4 population model with all couplings, and then discuss this in a more biological setting. But I don't see here more violations or of assumption or whatever than people would argue already for the Amari model. Again, this kind of structural stability, that you have this perfect symmetry, is biologically totally unrealistic. If you say, okay, we can live with this, and as an approximation, we can do a good job, I would say, okay, this local coupling here, which then allows you to reflect in the bump shape also some input characteristics, is a nice feature, which then in the application helps you to do things that you cannot do with the Amari model. But that's the message.
Okay. Good.
But the basic. Sorry.
Yeah, I was just gonna say, I think we probably need to move on in the interest of time, because we only have now 25 minutes left before people have to go. So maybe we can pick up this discussion later. I think you put some interesting ideas on the table for sure, and it'd be fun to loop back to them down the road and kind of deconstruct this discussion a little more.
Okay, good. So thank you again.
Yeah.
So we have on the agenda this social media issue, the Humpty Dumpty. I think again these modules can stay for later. Maybe these are the 2 most important ones.
Should we do the social media first?
Yeah, let's maybe do that first. Who wants to take the lead on that? Is it Minsiak or?
I can certainly show what we have right now.
So maybe even it would be the best perhaps to first explain the news item on the web page, and then how one can share that, right? Or is that the right idea?
Yeah, maybe for the dynamic field theory upset, Claudia can show that, and then I can show how the aggregator works and so on.
Yeah.
Yeah, I can do it.
Do you want to do that? Should I share? You want to share the screen?
I'm sharing. I'm just opening the web page. Sorry.
My Zoom is stuck here.
I think we are still recording. I'm not sure if you do that.
Sorry, I stopped sharing. I don't know how to get out of this. So now you should be able to. Okay, good.
Yeah, does it work? Do you see the web page?
Yeah.
Here's the new news item that Gregor published yesterday. So it's
we do have a news item feature now on the webpage, right?
yes. So if we go to the, if you already have a profile, of course. If you don't have a profile, you can always send me an email. And if you go to your back to the dashboard, it's not as complicated looking for you because it's the admin dashboard. If you go to content, and then you have the news menu here. Currently, I don't have any news, but I can show you also the
maybe
news.
I can just show.
Yeah,
exactly.
but since I'm an admin, I can.
We need to explain how. I think we should make a tutorial on how to do that.
Yes.
But maybe not now. Just to say that we do have this news feature on the webpage where one can also link to files and to videos and to anything. We can further improve how to do that. And we thought that would be the basis for a tweet or news item so that you can refer back to that. So people can find anything associated with that news on the webpage. So the first step when you want to make a tweet or whatever it is would be to create a news item on the webpage. And so we should make sure that you all know how to do that and that we can get your feedback to improve the process. Maybe we could schedule a tutorial on that maybe next time. So it's actually very easy, but still, so it can be a little bit of some little learning curve, perhaps.
So now if you have this added news here item, we can also, that was the wrong one. So here, so we now have this item here and we can copy the URL. And now I think that Milja will show the rest. So.
Yeah, so then the idea would be to make posts simplified for text and the posts in different social media platforms that we have. And for that, the idea was that we would have some kind of a social media aggregator so that we don't have to do this for all different platforms that we have. But then we can just generate a single post within the aggregator, and then that will take care of posting to multiple channels. So for now, we just have chosen one provider that does that. And then we have created an example post. So I don't think we have to do the tutorial right now, but I just show how that works, right?
Mm-hmm. Yeah.
So this is the demo or like the provider that we have chosen for. And then you can just easily make a single post within this aggregator, and then it will automatically create posts for different social platforms that we have. So for example, we did this now for Twitter and for LinkedIn. And you can see if you go to the account of dynamic field theory that we have a shorter text of the news item that is on the dynamic field theory org. And then we link back to the dynamic field org news item.
And so this shorter text you wrote in the aggregator.
Yes.
Mm-hmm.
It's actually just a shorter version of what you wrote. So
I see. Okay.
And then if you click on that, then you will be linked back to the dynamic field theory or news item. So that's the idea is really that the news item is where the actual content is, and social media is sort of the advertisement platform to, create attention and so that people can check it out, and you can see that the same thing has been done in the LinkedIn as well. So yeah, that's basically it.
And so would the idea be that one of us works with this aggregator for any news item on the web page, or would every individual do that? So
my understanding was that since this is quite easy to use, that we don't really need admin or anything like that, but anyone can just do this. we would probably just share the account that we have, and then whenever someone has anything to post about, then they just go about it.
Okay. Mm-hmm. Mm-hmm.
So I can then, so I just went on to X, annoyingly, formerly known as Twitter, right? And I do see that post on Twitter. So then to do the social media game, we all have to then ideally go in and amplify that by reposting, right?
Right.
So then do we need to kind of, so I'm just thinking about the mechanism. So I go in, I create a news item on the web page, and then I would log into the social aggregator or whatever it was and create a smaller version maybe of that post and push it. It'll push it out to Facebook and Twitter and blah, blah, blah. And then do I need to then email the DFT community and say, hey, everybody, this just went out. Could you please amplify it? Or, because see, the problem for me is I'm not on Twitter that often spontaneously.
I see. Yeah.
Yeah,
I would-
I think
I would
it's a good
miss that
idea.
Um,
Yeah, I think it's a good idea. That's what people do in my institution. When they
Yeah.
post something, then they send an email to everyone. Hey guys, like it, share it.
I see.
It's safer than it gets.
And
lost.
in that email, Julia, would you then list in that email all the links to the different media?
Ideally, yeah, or to your favorite one.
Just to make it easy to basically
So they
click
can
on it.
just click on something.
Exactly. So it's one
Right.
click. Mhm.
And so, Minchok, if you're in this aggregator, is there some easy way to export the links?
I'm not sure about that, but like getting the links to the article shouldn't be too hard. You just click on it and you have the link. So
Yeah, exactly.
Yeah.
I see. Yeah, I think that's great.
And John, that might be also a question. Actually, you said that you have somebody in your lab who did a really great job with the Facebook, and maybe ask them for the strategies they use to, not just posting but disseminating the posts.
Yeah, I did actually ask her, and her response, unfortunately, was complicated by the fact that Twitter is dying a slow death here. So she's now trying to figure out, are people going to migrate to Threads, or which new social media systems are people going to be using? So I think the landscape is changing a bit. But maybe the first step for us is just to get into the habit of, maybe Minsock or Raul or whatever, whoever's doing this, if you could kind of give us a little roadmap into what you'd like to see us do. Like Larissa and I have a paper coming out in child development in the next couple of weeks. We'll try to do that.
Yeah.
And
Good.
just kind of, let's see if we can iterate through a couple of examples, and everybody amplify it on like Facebook and Twitter, and just.
So maybe we could have 2 tutorials, one brief tutorial on how to create a news item on the web page, and then a tutorial on the aggregator, how to use the aggregator.
Yeah.
We even do that next at the next meeting.
Yeah, that sounds great. And if we can record that, then everybody who can't make it.
We wait for John to have the paper and Larissa, and then maybe we can just do it. Post the items and use that as an example to get started with a tutorial.
This news item I wrote is about a paper with Daniel and Mathis Richter, and we thought that's like our trial balloon to try that out. And then we could do another one for another. Each lab could do one so that they go through the procedure once.
Right.
We were thinking ideally that we would actually probably need like at least one post each week. Ideally, even like if it's possible, even more, to get a critical mass of flow going on, because you need to have something on there to really get started with this social community. So
yeah, that's a good idea. Like maybe we could even like script it out for a couple of months. I mean, it sounds painfully strategic, but that's kind of what you need to do. Like make a, you know, we could make a calendar and say, you know, think about the news that's coming out from your lab over the next couple months, and let's slot in who's doing which week, and then we can see which weeks are gaps and try to come up with what news item would fill in that gap.
That's good. We could make it part of this meeting to announce, and I'm going to have a news item here or there.
Yeah.
I witnessed this here at the Institute where we have a news item on the webpage, and you know, sometimes somebody just put up something and then next day I have something else and I don't want to override it. And then, you know, like I wait a couple of days, or that's where one could coordinate it, that we space it a little bit.
From what I saw, the aggregator also has like a calendar function, so you can try to like write the post.
You can schedule.
Yeah, you can schedule it. So
that's brilliant. Yeah.
Cool.
So I think we you know, you chose this. We could talk about how to pay it. I think unless this is this, you know, I was a bit shocked by. It has to be something that we can actually really pay. I have to talk to you about that. I mean, in terms of technically how to make the payments. But if that's a good choice, then we can just go with that, and then we should run through this for some of us, you know, make a little video perhaps about it, and then we can get going. That's good.
Yeah, sounds good.
So on the webpage, we talked to Raul that might be useful. So currently you can have a little text, you can have some like a visible icon, and you can add some photos. I took photos from the paper, for instance. And in the text, you can add links. There's like a kind of obvious editor. At links, currently we look into how to make the links more salient so that people really find it when visually, because currently you have to put the mouse pretty close to the object to even see the link, or it's a very subtle change in contrast that someone like me can't see. But we might be tuning this, and if you have suggestions, we can improve that. You know, for instance, links could be to videos also that we have, you know, on the YouTube page. So we should actually also make a tutorial on how to upload a video on the YouTube page, perhaps, right? Make sure that everyone has the password for that. I think we should. Yeah, I can do that then.
Or if we had some central, like on the Google Drive, some central place where we can
some instructions
and store the password information or whatever. I always have that. Like I can never remember the password for the DFT YouTube channel or whatever.
Exactly, and I have to find it.
Yeah,
I'm logged in now, but
but I think that the plan was to also use the aggregator to upload videos to YouTube, so everything should be in one place.
One can do that. Yeah. Okay, that's good. Okay.
Yeah.
Of course, best. Yeah.
And maybe to just briefly answer Gregor's question about the links, probably it's going to be best to use the conventions like on Wikipedia, where you have the links in a certain color that's pop up more, and if you click on them, they change color, and I think one is like bluish and the other one purplish. So they're like standards that are recognizable.
Okay. Yeah. Can we do that, Raul? Make the font color.
The font color of
of the link, where the link is.
Yeah, you can change it, but the link is currently underlined, so it's already quite visible now.
You already changed it. Okay.
Yes.
I'm visually impaired, so I'm maybe the worst participant in that study. Okay, I see. Great. Yeah.
I have another question. How is this? What about actually the Wikipedia page? I think something which is more like also not so much news, but more like something growing and more.
Yeah. So Lucas started that. He produced the text. So he knows a little bit about the procedure. He has become a low-level editor or something. I don't know exactly the status. He's not here today, and he thought one should start with a very small thing because the higher-level editors need to accept it, and it takes a couple of weeks for them to accept it. And when I then understood that, then I did criticize a little bit his text because I thought it had some problems if it stood alone. And we agreed how he would revise that. I don't know where that stands right now, but his goal is to correct that and submit that. Maybe he already did that, and wait for approval by these high-level editors. And as soon as it's approved, then we all can just go in and do stuff.
Okay,
I mean,
cool.
we might then need some tutorial how to actually do that, but he could do that for us. So in principle, that's on track, except that I haven't talked to him about that for about 2 weeks.
Okay. But there would be, I don't think that like this multiplicate, I forgot the word that you use. I don't think it connects to Wikipedia. So I think that would be growing on its own time scale and differently.
Yeah, I don't know so well. I mean, you can refer to Wikipedia, I guess, in anything you write. I don't know.
Yeah.
Yeah, but for example, as we, you talked about the modules, as we create modules on the YouTube channel, we'll then want to have those be news items to release them, and we'll then want them to be linked into the DFT webpage, and we'll then want them to be linked into the Wikipedia page.
Yeah.
Right. So we're kind of creating a whole universe of content here.
Maybe I would like also to volunteer, maybe help them more like with the Wikipedia page. I did something like for internal groups when I worked at DLR for internal collaboration, maybe presented. It was not, so editing was a little bit different, never like for general Wikipedia where everybody can see it, but like having this internal network structure and linking to posts and keeping it updated. I will gladly work there with Lucas maybe.
That would be great. So maybe I can point Lucas to you.
Yeah.
Is it? Should I use your personal this?
I think Evelina at dineva.de. So it's a German address. So first name at second name and then DE for Germany, which is also my initials in a way.
Is it? But is it HHU or no Gmail?
No, Evelina at dineva.de.
Wow. Okay.
Works as well, but I have so many emails there that I lose some. I overlook emails on Gmail constantly.
Okay. Well,
So
is it like this? I just.
Yep.
Oh, cool. Okay.
That's my permanent safe address.
Okay. So I'll try to establish a link between you and Lucas, who hopefully will be here again next time. Good. So I think we have a sort of plan. Maybe we can really try to do in 2 weeks already start these tutorials.
Yeah.
In the meantime, we will have moved ahead to make sure that this is the aggregator we can pay, and do this one item, get that item out, and then we'll use the alert through the email list. That's probably a good thing that we also can get feedback. If you have any feedback where you find it odd, you can just write back on that email list to me or to or everyone as you wish.
Maybe you can, when you're going to send out the email for sending out the minutes anyway, maybe you can also already mention that now we have this running, and then you have your first news item there so that people can retweet and
okay. Yeah. Okay. That's good. And that helps me, and I can make sure I understand this. So maybe we should talk about that tomorrow, about that aggregator and how to pay it. Good. We have 4 minutes left. So should we talk about Humpty Dumpty also next time?
Sure, that's fine.
Yeah.
And then, if people have any initial thoughts, I'm happy, we can then do some thinking over the next couple of weeks.
Can you say that again?
If anybody had a chance to read it, I'd be interested in initial thoughts.
Yeah. So we could make sure that next time we discuss it a little bit at least.
Yeah.
Make progress on that. So maybe we don't pick a scientific topic for next week so that we really get
it sounds like
focus on this.
Yeah, we have an
We're
accumulation.
naturally drawn into the science, but we need to also advance on this. And we have a whole week in Norwich, a subgroup of us, so we can also sort of think a little bit about planning.
Yeah, sounds good.
Good, great. Appreciate everyone showing up again. It's really very encouraging. I really appreciate that. So got a lot of things done today, and thanks Wolfram again for giving us
thanks Wolfram.
And actually, I did already download your papers while you were talking. Good. Okay, so see you in 2 weeks.
Ciao.
Great.
Bye.
Bye.
Everybody.
You.
Bye-bye.
Bye-bye.